Hey everyone, today we'll study about Grignard's reagent. See, Grignard's reagent, by short form, it is RMGX. Okay, it is called as RMGX. So, usually that is formed when you take an alkyl halide and react with magnesium in the presence of ether at around 0 to 5 degrees centigrade, which will result in making a compound like this RMGX. Okay, generally, if we have a metal directly connected, if metal is directly if metal is directly connected to carbon, metal is directly connected to carbon in organic compound, it is called as organometallic compound. Therefore, Grignard's reagent is one of the organometallic compounds. Correct. Well, what is the main role of organometallic compounds? They are carbon base and nucleophiles. Okay. Organo organometallic compounds act as carbon base or nucleophiles. Nucleophile. In short, you can check it out this way: R minus Mg plus and X minus, like this. Okay, this is how you will have. So you could imagine that R here is acting like minus, which means it can act like base or it can act like nucleophile. Okay. Now reactivity of various organometallic compounds. If I compare the reactivity of various metallic compounds, that would be proportional to first polarity, how much polarity it is able to generate. So polarity of carbon, how much carbon anion character it is getting. Okay. Polarity of carbon metal bond. Carbon metal bond. Okay. Second is electronegativity of metal atom. Electronegativity of metal atom. Okay. So if you notice the reactivity order, I'll say that R minus K plus. This compound will be much stronger as a reactivity compared to that of R minus Na plus, and then we have R minus Li plus, then RMgX, then RZnX, then R2CuLi, which you call it as Gilman's reagent, and R2CD. Correct? This is R2CD. Clear? And if you notice the reactivity based upon X reactivity, that is halogen's reactivity, then iodide will be more reactive than bromide, then chloride. Okay, weaker the bond, better it is. Clear? So basically, how it is happening is like this, where you have, if you notice the mechanism here, it is like this: R, X plus Mg, right? In the presence of dry ether, we are able to generate RMgX. Okay. Here Mg is releasing out two electrons in ether. Okay. And these two electrons will attack on alkyl halide. These two electrons will attack an alkyl halide. to remove out that halogen group. So as it attacks here, so it will get this as R minus plus X minus. Okay. Now you could imagine magnesium getting surrounded by this. Okay, magnesium will be completely surrounded by this. So we will have something of this sort, Mg2 plus surrounded by solvent, that is from the lone pair support you will get from the solvent here like this, and at the same time R delta minus support is observed like this. This is how magnesium is going to get surrounded. So this is the bond which has been formed between R and MgX. This is polar, this is polar, sorry, here it is X minus, X minus, X minus, okay, it's delta minus. So here it is polar ionic bond, while on this side it is polar covalent bond, polar covalent bond. So that's how, because it establishes this polar covalent bond, we usually see that reaction, I mean, we usually see that it is forming uh, RMJX will have, slight negative charge on R and positive charge on magnesium. Got it? I guess this point is clear, everybody. Now, now this R could be any kind. It could be alkyl, vinyl, alkynyl, phenyl, allyl, benzyl, any of the form. Okay? This R could be alkyl group. It could be any aryl group, allyl group, benzyl group, and so on. It's not necessary. It has to be only alkyl. Okay, got it. Next, we need to understand how many compounds we have which will make this Grignard's reagent or which will not make this Grignard's reagent. Okay, let us see as a question. Number of compounds, number of compounds, okay, which form, which form Grignard's reagent, which will form or which will not form. First one, if you notice, in case if you have Cl and OH, in case if you have Cl and OH, then if you treat this with magnesium and ether, then problem here is, first you will notice that there is a formation of Grignard's reagent here, that is minus and MgCl plus and OH here. Okay. But immediately you will see internally this H plus can be called up here. So what is the product now you will have is H will come here. We'll get this as O minus and MgCl plus. Now this is not a Grignard's reagent. Not a Grignard's reagent. Clear? Grignard's reagent has to be RMGX. So you could imagine if there is any kind of acidic compound present, like acidic hydrogen present in the molecule, then it is very difficult to form an Grignard's reagent. Clear? Second case, suppose if you have two chlorides like this, and then I'm treating with magnesium and ether. Again, at one place, it will form R minus MgCl plus, and the other side we have Cl. So internally, this negative charge will push and try to remove this chlorine. Thereby, we will get actually CH2, double bond CH2 plus MgCl2. So we are not getting a Grignard's reagent either here. Clear? So if you have two chlorides, two bromides adjacent to each other, then also you will not have any Grignard's reagent formed. Okay. Third case, if you have only phenyl chloride Here there is no problem. You will notice that minus will form, Mg plus Cl minus will form. So here Grignard's reagent is forming. Okay. Fourth case, if you have allyl chloride, in allyl chloride, Grignard's reagent formation is not observed. So no reaction here. In allyl chloride, we will not see any reaction form. Fifth one, if you have chlorine here and bromine here, okay, like this, and then I have magnesium and ether. Reactivity wise, because magnesium is more reactive, you will get formation at this location. So it is a Grignard's reagent, okay, and it is forming at bromine place, okay, clear everybody? But see, when I said this is happening for chlorine, can the same thing can happen for bromine here, okay? So that is, if you have only bromine and you're treating that with magnesium and ether here, so in that case, you will not see no reaction here, sorry. For chlorine, yes, it is relatively more reactive, but in case of bromine, sorry, not bromine, I meant to say here Cl, bromine and Cl if you have, okay, then it is not reactive. How is that? See, problem here is again the same logic. So first we will get minus charge here like this with Mg plus and Br minus, okay, and we have Cl here. So internally again this will push, this group will come out. So thereby we will get a benzyne intermediate. We'll get a benzyne intermediate and we'll get Mg, Br and Cl like this. So instead of getting Grignard's reagent, so here no Grignard's reagent is formed. Okay, clear everyone? Right. Next, if you have 1, 2, 3, 4. So Br is here, 1, 2, 3, 4, and one more Br is here. Okay. So if you take in this case magnesium and ether, here also we'll get 1, 2, 3. Okay. Which we have 1, 2, 3, 4. Yeah. If you have 4 and above, there is no problem in terms of Grignard's reagent. So 1, 2, 3, 4. So in this case, Grignard's reagent will be formed on either side. You'll get this as minus MgBr plus, and here we will have 1, 2, 3, 1, 2, 2, 3, 4, and then 2, 3, 4. Yeah. And then we have minus and MgBr plus. Okay. So Grignard's reagent will be formed in this case. But in case if you have only 3 carbons, 1, 2, 3 carbon, and then we have Br here and Br here. In case of 3 carbons, magnesium and ether, so first we will get a minus charge forming here with MgBr plus, and internally this minus charge will push here and remove bromine to form this as cyclopropane, okay, plus MgBr2. So you would notice that 3-membered ring will not be stable here. So that is what you'll notice, that it will not form any kind of Grignard's reagent in this case. Okay. I guess this idea is clear, everybody, right? Yeah. Even if you have a triple bond, let's say 1, 2, 3, 4 iodine here, and then you have a triple bond here. Here also, if I take magnesium and ether, so first we will get minus and Mgi plus here, and then there is a triple bond here. So triple bond, you know that hydrogen is sufficiently acidic. Because hydrogen is sufficiently acidic, this hydrogen will move here. So thereby we will get this product as C triple bond, triple bond minus Mgi plus, this Mgi plus, and this carbon is continued with another carbon here with CH3. Okay, this is how the product will be. So it is not a Grignard's reagent anymore. Clear? Grignard should be only as RMGX, right? So it cannot be a Grignard's reagent in this case. Okay. So I hope you guys got a fair idea, like in which case Grignard's would happen and in which case Grignard's will not take place. Okay. So whenever there is any internal push here, it will not happen. Okay. Another thing where Grignards cannot be formed, suppose if you take, for example, oxirane like this, okay, and then you treat this with RMGX, okay. RMGX generally is stable in ethers except for this ether. So the minus part and plus part, if you notice, this minus part will attack here, goes for an SN2 reaction here, thereby you will get this as R combined with these two carbons with O minus and MgX plus. Okay. So therefore we can say it is unstable in oxirane. So three-membered cyclic ether, it is unstable. But if you have four-membered or if you have five-membered, right, then it is definitely stable. Okay. Four-membered also it is unstable, but five-membered ring it is stable. So if you notice this one like this, and then you treat with RMGX, then it is a stable solution. Stable solution. No reaction will take place. Got it? I hope this part is clear, everyone. Okay. What is the main role of RMGX? I hope all of you got this. Now, sir, in the case of four or above carbons, does GR form either side, even not mentioning excess of reagent? Yes, sir. Okay. So if you have more than four carbons, on both sides, RMGX would happen. Generally, you start off with one side of it. Clear? If it is excess given, you mention it on both sides. Otherwise, if you put it in either side, it will be stable. Okay, right. Next, let us see what are the reactions of Grignard's reagent. Reactions of Grignard's reagent. Okay. First one is about nucleophilic addition. Nucleophilic addition reactions. Wherever there are aldehydes and ketones, it will always attack on them and get added up. So that is, if you take RMGX plus HC double bond O and H, right? So then on, you'll notice that R minus will attack on this carbon here, and we will get this as RCH2 O minus, because as soon as it attacks, this bond will move on to oxygen, O minus and MgX plus. This is what has been formed. And if this has been followed by hydrolysis, that is, if you take H3O plus on it, so we will get this as RCH2OH. What we are getting is 1 degree alcohol. 1 degree alcohol plus magnesium would become 1X and 1 OH here. So this is the product you will get. Okay. So I hope all of you understood what is going on here. Similarly, this is for formaldehyde. And if you take any simple aldehyde other than this, here I'm taking some R dash. So this time the reaction will be R, CH, one more R dash here, then O minus, MgX plus, if it is followed by hydrolysis. So we will get this as R, CHR with OH plus MgX and OH. So what we are getting here is 2 degree alcohol. Okay. which means if you take only formaldehyde, we'll get 1 degree alcohol. If you take any other aldehyde, acetaldehyde or any kind of aldehyde, then we will get secondary alcohol. Next, if you have RMGX treated with ketone, R dash C double bond O R dash. This is ketone. So when you add it on ketone, you will get this as R C R dash and R dash here with O minus MgX plus, that on hydrolysis, acidic hydrolysis will give you alcohol plus MgX and OH. This is what you will get in case of nucleophilic addition on this case. Okay. Generally, if you take the rate of reaction, less the crowded, more is the reactivity. That means formaldehyde is much more reactive compared to that of acetaldehyde, okay, compared to that of benzaldehyde, compared to that of ketones, simple ketones, then benzene-based ketones, and finally two-side benzene ketone, okay, diphenyl ketone. Yeah, this is how the rate of reaction would be. Okay. So rate of reaction mainly depends upon, like, how much steric crowding it has, right? So rate depends on steric hindrance, on carbonyl group and plus side and electronic effects. That is whether we have minus I, plus M or minus M. Depending on that, reactivity can change. Okay. Right. This is about the first reaction, like where you can see, where did I start here? Yeah. First is nucleophilic addition reaction. Second reaction is also a nucleophilic addition, but this is on reaction with carbon dioxide. How does Grignard's reagent react with carbon dioxide? So if you take RMGX, Grignard's reagent, and attack on carbon dioxide, right, like this. So carbon dioxide will have delta positive and delta negative here, which makes this R to go and attack on carbon. Therefore, we will get RC double bond O minus MgX plus, because as soon as the attack happens, the pi bond will move on to oxygen. And once you get this form, after hydrolysis, we will get R C double bond OH plus Mg, X and OH. So what we are getting is carboxylic acids. So when you treat with carbon dioxide, we will always get carboxylic acids. So remember that. Grignard's reagent, when you treat with carbon dioxide, we will get carboxylic acid. Next, reaction with acid derivatives. Reaction with acid derivatives. Okay. Here, first one, let us see acid chlorides. So R MgX, right? If you treat this with R dash C double bond OCl, this is acid chloride. Acid chloride is a derivative of acid. So if you treat with acid chloride here, you will notice that this R minus is attacking. R minus is attacking here. So the the product which you'll get is R C double bond O R dash plus chlorine will go away. So we'll get Cl and X. If you notice the mechanism here, you will see that R dash and MgX plus like this. When we expose it to acid chlorides, so this R dash would attack first. This O minus will move. So we will get this as R dash C, R dash C, O minus and Cl and R. Now this O minus will close to make a double bond. Cl minus will release. Thereby we'll get this as R dash C double bond O R. So what we are getting is ketones. Okay. So here this is a first step which we have done. So this is using one equivalent. So remember that using one equivalent of RMGX. So if I use only one equivalent, I'll end up at ketone. But if you follow further, if you have one more equivalent, then it will convert into alcohol. So that is, if I take one more mole here, RMGX plus RC double bond O, R dash, then I'll get this as followed by hydrolysis. Then I will get this as RC, R and R dash here and OH plus Mg, X and OH. So you notice that this is using two equivalents of RMGX. So if I use two equivalents, I'll end up at alcohols. If I take only one equivalent, I will end up at ketones. Got it? I hope this point is clear, everybody. Same logic applies to other acid derivatives as well. So suppose if I take R MgX treating with R C double bond O O R dash O R dash, this is ester. So when RMGX is treated with this one as well, okay, let me take this carbon as CH3 just for our convenience, CH3. So now, first R will attack on carbon, makes this as O minus CH3 and OR dash. So as soon as it closes here, this group will come out. I'll get this as RO minus MgX plus R C double bond O CH3. So this is using one equivalent of RMGX. Using one equivalent of RMGX. So if I use the second equivalent also, so RMGX plus R C double bond O CH3 we have. If we use one more equivalent and then do hydrolysis, we'll get this as R C R C R here with CH3 and then OH, right? This plus, if you notice that this is also RO minus, if you add it in water, you'll get that as alcohol, ROH, R dash OH. Okay. So this is the final product using two equivalents of RMGX. So if you use one equivalent, end up at ketones, two equivalents, you'll go up to alcohols. Got it? This is the product formation you will notice. Okay. I hope this point is clear, everybody. Let us see some questions here on this basis, right? First, let me complete the all acid derivatives. Suppose if you have R C double bond O NH2 amide, okay, and on amide we are treating with RMGX, okay. So what you will notice here is that R minus, instead of attacking on C double bond O, it will directly take hydrogen from here. So we will get this as RC double bond O NH minus MgS plus we will get this as RH. Okay. Because uh, when it comes to Grignard's reagent, the first reaction which you need to check out is about acid-base reaction. If only acid-base reaction is not possible, then the other reactions would be happening. Okay. So first, as long as the acidic hydrogen is present, that is the first priority which we need to check. Okay. So based on this, I can say the product will stop here only. So if you like kind of further hydrolyze this H3O plus, again we will get this as RC double bond O NH2 and Mg X and OH. Correct. So we will not end up getting any alcohols here like that, and we will simply getting this as alkenes because it is more acidic. Okay. Similarly, if you take RMgX and treat that with anhydride, C double bond O, C double bond O, R dash and R dash. So this time R will attack on this carbon. This bond will leave if it is one equivalent. For one equivalent, we'll get this as R C double bond O R dash C double bond O R plus R dash C double bond O minus and MgX plus. Got it? And if you try to deal with one more mole here, so this will again react. This is only using one equivalent of RMJX. If the question is only one equivalent, students, you'll end up here only. You will not go for the reaction. But if it is given nothing, you will react once again with R dash C double bond OR, and you'll get this as R dash CR and R with O minus MgX plus. And if you hydrolyze this, because you have this molecule also present in the solution, right? This molecule is also present in the solution. So these two followed by hydrolysis H3O plus will give us R dash C R and R here with OH plus R dash COOH. So these are the final products you will report when you have more than 1 mole of Grignard's reagent. This is with anhydrides. Okay. Check out similarly with cyanides here. So RMgX, if you treat this with any cyanide, let's say CH3C triple bond N, this is a cyanide we are going for. So R will first attack on this carbon. We will get this as CH3 C C with R double bond N minus MgX plus N minus and MgX plus. And now problem here is it is after one equivalent, correct? Even if you want to do it from second equivalent, right, RMGX, the attack of this RMGX is not possible because already there is a negative charge present here. So that negative charge will not let anything push here. Earlier, what is happening was that negative charge was, that OR group, this group was good leaving group. That group left and we got ketones. But here we are not able to get something like ketones easily with that. Okay. So the second mole of RMGX attack is not possible, right? So this is what even in excess of RMGX. So even if you have excess of RMGX, you'll only stop it here. So further reaction is not happening. So now once you get this R double bond N minus MgX plus, and this if you hydrolyze it, we will get CH3C double bond OR. Basically, this will get hydrolyzed. This entire group will get hydrolyzed. Double bond will break here. It will become double bond O with the water added. And this is the final product. This is the final product. So in cyanides, we will never get alcohols. We'll only end up getting ketones. Clear, everybody? These are all the reactions with acid derivatives. Okay, how the reactions of Grignard's reagent take place on acid derivatives. Okay. Now, if you notice few examples, let me take one question here. So if you have different compounds, then how do we respond? Okay. So first, if the question is given like this, I have amine here and there is a chlorine here, correct? This is how it is. And then I'm treating that with magnesium and ether, correct? So if you have N here, H here with minus MgCl plus. So internally you would notice that this hydrogen is sufficiently acidic. So that will migrate on the other side. So we will get this as N with H here, this getting minus and MgX plus. So this is the final product you will report. So here we will not have any, Grignard's reagent directly. But now if you notice that this, if you are trying to react with this uh, aldehyde, let's say, if you're trying to react this with aldehyde, so then the attack will be from the nitrogen end, okay, not from the carbon end, it will be from the nitrogen end. So we will get compound like this, where we have N connected to CH2O minus MgX plus, which on hydrolysis, you will get this as N with CH2O. So this is the final product you will have. I guess this part is clear, everyone. Yeah. So whenever we have this kind, we need to understand that RMGX would act slightly differently. Okay. Now, not every ketone will be reactive with RMGX either, depending upon the crowding, how much amount of crowding it has. For example, to take another example here, suppose if you have a group like this, double bond O and a group like this is extremely crowded one. So extremely crowded on the ketones. So if you notice RMGX in this case, no reaction will take place. Similarly, if you have benzene with too much of crowding on the ortho position like this, okay, and then we have C double bond O, and this side also a lot of crowding is there. So these kind of cases, we will not see any reaction happening. Okay. Even if you have two benzene groups with a lot of substitution on ortho product, like let's say I have NME and ME here, right? NME twice. And then this is connected to C double bond O, right? Which is again connected to benzene with methyl and methyl here like this. So this is heavily crowded. So RMGX in such kind of cases will not make any reaction with ketones. So ketones should be less crowded always. Okay? Then only the reaction will take place. Clear? Now, typically, questions that are asked from Grignard's reagent is about how many moles of aldehydes or ketones will be consumed. Okay, so question will be like this: how many how many moles of X, moles of uh, RMGX, how many moles of RMGX in the following reaction are consumed. Okay, reactant given is like this: we have benzene here, right? And then we have double bond O, Cl, and we have double bond O, OET, like this. Okay. Then I have OH here, SH here, and then we have a triple bond CH here, like this. And I need to consume some, let's say, X moles of RMGX are being treated. Clear? Right. So just by watching this, you should be able to figure out that how much number of moles of RMGX are required. Notice this. First, if there is an acid derivative, that is, if you have acid, chlorides, esters, anhydride, we learned that at least we require 2 moles. So therefore, here we require, for this case, I require 2 moles. For this case, I require 2 moles. And here, one hydrogen will be consumed because all acidic hydrogens are consumed by Grignard's region. This will be consumed, this will also be consumed, right? So total number of moles are how many? Okay, three acidic hydrogens are present. There three will consume, and C double bond or Cl will consume 2 RMGX, while C double bond or OAT will also consume 2 RMGX, right? So consume 3 RMGX here. So total number of RMGX consumed are how many, right? 7 RMGX will be consumed. So 7 moles of RMGX are consumed. Is this clear, everybody? So we just need to check out and let us let know that how many moles will be consumed or how many moles will be remaining. Everybody understood that? So this gives us one important clarity that whenever you have RMGX, you have RMGX, and if you are treating that with any acidic hydrogen, okay. So where do we find this acidic hydrogen? Water, okay. If you have alcohol, if you have ammonia, NH3, next. If you have any carboxylic acid, RCOOH, or if you have amines, amines with, you know, hydrogen, acidic hydrogen on it, RSH, any type of RSH. Next, if you have double bond O and double bond O, you can see this is at the center, it has an active hydrogen, active methylene. Active methylene can also be used as sufficiently strong acid. Next, we have aromatic aldehyde like this. This will also give away H plus because here this is an active carbon and it has two active hydrogens. Those hydrogen can be involved for RMGX reaction. Okay. Next, amide also. Take R C double bond O NH2. So if you notice in all of this, there is sufficiently, strong acid present. Phenol also, I forgot phenol. PHOH, phenol. So you can see we have alcohol, water, alcohol, ammonia, acid, amine, SH, this one, this one, this one, this one. All of them have sufficiently acidic cases. Okay. What does active carbon means? Active carbon is those carbon where you have active hydrogen, which means hydrogens which are sufficiently acidic in nature. Okay. So you can break the bond between carbon and hydrogen there more easily. Clear, beta? So taking in all these cases, the product which you will get is RH because it will take hydrogen from all of these cases and convert into alkane. Okay. This can be used as a methane test. You can take CH3 MgCl. If you take this as CH3 MgCl, you react with any of them, you will get methane gas. You will get CH4 gas. I hope this point is clear, everyone. Yeah, right. As much as Grignard's reagent is concerned, this is how much you need to know from this topic only in terms of Grignard's reagent. Uh, um, whatever the questions, whatever the ideas which we need to learn is majorly this one. That is how good, whether they will form Grignards or not. These cases are important. Okay. So learn whether the Grignard would happen or not with those cases. Yeah. Now, slightly going ahead into this topic, right? We need to just kind of revise ourselves in case if you have SN2 type of reactions, right? What are those type of reactions which will happen? And I think I told you already that some of the reactions already are there in the assignment. But anyways, I will do some questions which are related to SN1 and SN2 type of cases. Okay. But as much as Grignard's is concerned, these are the reactions which you need to learn. Okay. Right. Next you see questions and concepts related to SN reactions. Sir, can you once tell cyanide case? Okay, check. In case of cyanide, here, if you notice in case of cyanide, first R has attacked here. So pi bond from this will migrate on nitrogen. So we'll get N minus Mgx plus R will come. Now, when the second mole is trying to come, since nitrogen already has negative charge, it will not accept one more pi bond onto it. Okay. So since it cannot accept, now carbon is also reluctant to accept R plus. So this attack is not possible anymore. Tanuj, clear? So because of which, since the second mole is not possible to react, no matter whatever you do, you will only end up at this molecule, even if you take excess of RMGX. So once you get this point here, now once you, from here, if you do hydrolysis, what is the product you'll get? Ketone. Now you might be wondering, sir, what if I react this ketone once again? My point is, once you do hydrolysis, there is no more RMGX left. All the RMGX will react with the hydrogen and convert into alkane, no matter how much excess you add. So you will not be have anything left to react with ketone anymore. So therefore, the final product you will report is only ketone. Any doubt there? Clear with it? Yeah. Now, usually, this concept of hard acid and hard base or hard and soft acid base theory is less useful for us, but sometimes it will help in solving simple questions. So I would suggest remember this one, a concept of HSAB, that is hard and soft acid bases, acid and bases. Okay, hard and soft acid bases. See, anything which is hard to polarize, they are called hard bases or hard acids or hard bases. So, for example, if you have hard acids means you will not be able to polarize them easily. That is cations which are hard to be polarized. Polarize means I cannot pull their charge or make them to uh, make their make their charge to spread across. So they are extremely concentrated. So cases like lithium plus, beryllium 2 plus, magnesium 2 plus, aluminum 3 plus, like this. These are all hard acids. Correct? These are called hard acids. Remember that. Next we have soft acids. Soft acids. Okay. These are cations which are easy to be polarized. Easy to be polarized. Okay. If you notice the example here, CS plus or any carbon based plus charge, carbon plus charge here. Okay. Uh, if you have silicon, some kind of silicon getting plus charge here, and so on. This kind of cases, if you notice, that means these are all soft acids. Okay. Next, hard bases. Hard bases. Again, anions which are hard to polarize. Anions which are hard to polarize. Hard to be hard to be polarized. Okay. For example, F minus, OH minus. These are very small size ions. Okay. So when you have small size ions, very difficult to get polarized. Soft bases. Soft bases. Anions, which are easy to be polarized. Easy to be polarized. Okay. Example, I minus, Br minus, S2 minus, and so on. These are bigger in size also, and they are soft bases as well. Okay. And the basic principle here is HSAB principle. HSAB principle is, right. Hard acid will always prefer to bind with hard base. And same is the case with soft acid. Hard acid prefers to bind with prefers to bind with hard base, and similar for soft. So that means soft acid will try to bind with soft base. Okay. This is called HSAB principle. Remember that. Okay. So which are hard acids, which are hard bases, which are soft acids, and which are soft bases. Here, got it? Now, when it comes to, uh, you know, sorry, this carbon is smaller now, but my mistake. If it is complete positive charge, it is hard. If it is delta positive charge, then it is soft. Okay. Next, check out. Suppose if you go through an SN1 mechanism, so we will get this as something from here. What we do, if you have a leaving group, we will make a carbocation. A complete carbocation means this is a hard acid. This is a hard acid. Okay. Since it is a hard acid, the nucleophile which we are attacking, right, should also be hard base. Okay. So that means any oxygen connected. So you know that, like water, for example, if you take water, it is oxygen connected. Like ammonia, NH3, nitrogen connected. So nitrogen connected, oxygen connected are hard bases. Okay, so that's why you will notice that SN2 is happening with water, alcohol, all of them. From the oxygen end, you'll always see oxygen getting attached with it. Okay, but if you have SN2 type of reactions where leaving group is not going completely, it is only generating delta positive and delta minus charge. Okay, in that case, the nucleophile which you are acting will be better with soft bases. Better with soft bases, right? Soft bases like I minus, N3 minus, ACO minus, correct? These are all the soft bases. So because they are soft bases, that's why SN2 is more preferable. Now we know that NH2 minus will not attack that easily. Okay, NH2 minus, OH minus will not attack that easily in SN2. Rather, they'll go for elimination reaction, isn't it? They'll prefer to go more for elimination. So in SN2, soft bases are more preferred. Okay. Don't mistake that soft means they are weak. Okay. Here, hard and soft is on the basis of polarization. Okay. So don't try to relate those two. Clear. Similarly, when it comes to in cyanide ion as a complete ion, if you notice, correct, this is a softer base because it is on a carbon base here, while nitrogen's lone pair is always harder base. This is a harder base here because it has more electronegativity. So less likely to get that is less likely to get what you say polarized. Okay. This is in cyanide. Next in nitro NO2 group here you will notice that N has a lone pair here, O minus and double bond O like this. Okay. Now compared to oxygen nitrogen, this is softer now. This is soft base. while the lone pair present on oxygen, that is hard base. This is hard base. Okay, clear? So now imagine if you have a 3-degree alkyl halide like this, and then you treat that with NO2 minus. If you are treating this with NO2 minus, and you notice that where does it attack from? If it is 3-degree 3-degree, then it will definitely make it, okay. It will definitely make it into carbocation. And if you have a carbocation, that is a hard acid. That is a hard acid. And O and double bond O. Now this time O minus is a hard base. So which will make a reaction now. So this is what the reaction will happen. So the product will be RON double bond O plus X minus. Clear now? That's why in case of tertiary, you'll usually see oxygen getting connected more easily. Got it? So even if you take, for example, if you take Rx plus AgNO2, the other day I wrote this, just to remind you what we learned here. If it is 2-degree or 3-degree, it will form carbocation. In that case, RON double bond O only is major. This one is major. The other part connecting from nitrogen to get this as nitro product, this is minor. This is minor. Okay. But if you treat this with KNO2, KNO2 is also ionic in nature, correct? So same logic here also. This will be if Rx is 2-degree or 3-degree. If Rx is 2-degree or 3-degree, definitely we will get this as, yeah. Let me rewrite this once again. Rx has 1 degree here. We write this as 1 degree. AgNO2 here. In that case, we will get R, in case of 1 degree, definitely RNO2 will be major plus RON double bond O will be minor, right? Now, same thing can be repeated again with KNO2. Now, in case of KNO2, it is always completely ionic. KNO2 is completely ionic because it is K plus and N minus, K plus and NO minus. So now what you will notice is here, right? For 3-degree only, you will notice this. For 1 degree and 2 degree, you will notice this. Correct? So in case of 1 degree and 2 degree, you will notice that NO2, NO2 is major here. Okay, NO2 is major and this is coming out to be minor. But if it is 3-degree, definitely RONO is major and RNO2 is minor. Done. So this is one area which you need to understand more thoroughly what exactly is happening there. Next, if you see the reactions of, I think we learned reactions related to, yeah, I think one area which students have asked me is that the other day some of them have asked me allylic substitution. Allylic substitution. See, in case of allylic substitution, what we need to think. Suppose if you have a double bond here, and then I have a chlorine group here. And if this example, if at all, I treat this with H2O. Okay. So I'm expecting this to go via SN1 reaction. Okay. So because allylic carbocation is more stable, I can expect that positive charge will be formed here and Cl minus will leave here. Because positive charge is forming, I can expect this to come as OH here, OH like this. and this is via mechanism SN1 because you're attaching on the same position. But due to resonance, if you notice that due to resonance, this pi bond, if it moves here, we will get this as double bond with positive charge. And because of this double bond and positive charge, we will notice that there is another product which we can form. This is on OH. Now, since leaving group position was here, now nucleophile is attacking on a new position, which is a resonance stabilized position. This is called as via SN1 dash. So this is via SN1 prime. This is via SN1. This is via SN1 prime. So I hope you guys understood which is what. Generally, SN in such cases, right? It all depends upon the solvent. Suppose if the solvent is water, which is highly polarized. If it is highly polarized salt, then major product will be this one, and minor product will be this one. Minor product will be this one. Reason being, this carbocation which is present here will be strongly held by the water molecules around it. So that's why the water will attack directly here. Less resonance. I mean, resonance will happen, but electron density will be more concentrated here. But if it is aprotic solvent, right, then this will be major product. But this is about allylic substitution via SN1 or SN1 dash. Now, if the same reaction is being given here, the same allylic substitution, but instead of H2O, we are taking OH minus, and OH minus is a strong nucleophile. So since it is a strong nucleophile, you will get these two products again, but this is via SN2, while this is via SN2 dash. The idea is the same. Okay. So now this time OH minus will attack on this position, pi will move here, and Cl minus will come here. And remember, major product in this case will always be SN2 dash. So this is major product and this is minor product here. I hope all of you understood how the allylic substitution works. Check if anybody has a doubt, let me know. Doubt there? Right. Next question that could be asked here, other than allylic, is about role of solvent in SN2 reactions. Role of solvent in SN2 reactions. Okay. This is one very standard question that you will always get in exam. Learn this carefully, everybody. Check. Suppose I have Rx as the alkyl halide and I'm treating this with Y minus. The nucleophile already has a charge. Remember this. So if it is Y minus, what do we get here? So we will get the we'll get the transition state as Y trying to attack R and X trying to release. This will have delta negative. This will have delta negative. So this is the transition state. This is a transition state. Clear? So if I say that effect of effect of rate on increasing polarity, increasing polarity. So I'm trying to figure out what would happen to the rate as the polarity is increased. Okay. Now what would happen in this case? Suppose if you increase the polarity, isn't it? If you increase the polarity, water will start attack. Let's say polarity as in water I'm taking as a reference. Okay. So water is highly polar. Imagine. Okay. If you take water in this case, right? What will water do? Water will stop this Y minus from attacking here, isn't it? Or the nucleophilicity will decrease. Since the nucleophilicity will decrease, what would happen to the rate? Rate decreases. So in the first case, what is happening, everybody? Rate is decreasing. Okay, I'll write it here. Case number one. Case number one, what you would notice that this is decreasing. The rate is decreasing. Why? Nucleophilic strength is been decreased by the increase of polarity. Second case, suppose if you have Rx and I'm treating that with Z, a nucleophile which does not have a charge, it has a lone pair, it does not have any charge. So now the intermediate what you'll form is Z delta positive, right? Because it is, uh, it does not have charge. Now it is giving lone pair. Then X delta minus like this. Okay. Now this is very crucial because you know that this does not have any charge. So even if you increase polarity, there is no effect on nucleophile. There is no effect on nucleophile. But if you notice that since it has positive and negative charge, increasing polarity will always helps it to develop more and more positive and more negative charge. So what happens to the rate now? Increases. So you can notice that rate of SN2 increases, rate of SN2 increases if your nucleophile is a neutral nucleophile. Okay. So rate of SN2 increases in polar solvents if your nucleophile is neutral nucleophile. Okay. Second, third. Next, if you have R, some kind of X plus, X plus. So instead of leaving group is neutral. Now leaving group has some charge. Plus, I took this as X minus. Sorry, Y minus. I'm taking this as Y minus. So in that case, what would happen? We will have this as Y minus trying to attack R. At the same time, R is trying to depart from X with some positive charge here, like this. Now the logic is the same. If you take it the charge per one, solvent water will, if water I took it as a reference, water will try to get across this one, Y minus. So both interactions will be very weak. They will not be able to interact because water is separating this side and this side. So the reactivity would be less. So what happens? In this case, it will decrease. So in this case, the rate will decrease. Fourth one, if you have R, Y plus, and then I added neutral ones, then I'll get this as Z delta positive connected to R, which is connected to Y, which is delta positive, like this. In that case, what would happen? Now you will notice that the Y is leaving from here, Z is attacking from here. This is not influenced by the polarity. Now, this polarity will increase. So basically, it is easier to break now Y plus, because water will surround this. Water, when it is surrounding it, the bond between R and Y will start breaking up more easily. Right? So this will decrease. Clear? So this instead of this nucleophile going and attacking here, the solvent itself will go and attack this one. The solvent itself will attack. So therefore, the rate due to this nucleophile decreases. Okay. So what have you noticed? In most of the cases, rate will always decrease except one case, except this case. That's why when it comes to SN2, most of the time we will prefer to go for aprotic solvent. Aprotic solvent is always better choice. Everyone understood that? Why we need to choose aprotic solvent? Okay. Okay. Next type of question which can be asked. I think most of the question types we have touched already. Let me just check it out if there is anything left which I need to touch on to. If we have been directly given a reaction with a reagent, what is the thought process we should have? Check out these questions. Suppose I have a tertiary chloride and it has been given ETOH. Sudden thought we should get is SN1. Okay. Similarly, if I give you Cl with ETOH and heat, thought should come as E1. Got it? Similarly, if I give you Cl and ETO minus, right? No heat given, ETO minus. That itself means it is E2. Next, if I give you Cl with ACO minus, ACO minus. Okay. So this is SN1. Why? Because it is a weak base and nucleophile. We should think in terms of nucleophile. If I give you Cn minus, that is NaCN. That means it's a strong base. You will think in terms of E2. Strong base, you will always think in terms of E2. Here, next, if you have um 1 degree alkyl halide like this. If you have 1 degree alkyl halide and you have NaH, I told you H minus will only do E2. It will not go for SN2 kind of reactions. Only E2. If you have Cl with aqueous NaOH, you will think only in terms of SN2. Correct? If you have NaSH given, also SN2. If you have ETO minus Na plus given, ETO minus Na plus given, okay, you will think in terms of SN2. If you have ETO minus heat is given, you think in terms of E2. If you have Cl, ETOH given, right? ETOH given, still you will think in terms of SN2. SN2. This is at primary position. So even with a weak nucleophile, you will only think of SN2. Okay. Then everybody, if you have been given Cl with alcoholic KOH, this wording is used. Alcoholic KOH wording is used. That means you'll think of E2 mechanism. In this case, you'll think of E2. Correct? Next, when it comes to secondary cases, okay, if you have Br and I have NaH, that is H minus, you'll think in terms of E2. If you have Br, correct, and aqueous NaOH is given, clear? You will do SN2, this one via SN2 and elimination via E2. But major product, as long as it is aqueous, means major product should be given to SN2. Okay. Next, if you have Br with ETO minus Na plus, ETO minus Na plus, in that case, we'll get this as OET. This is via SN2 and alkene via E2. And this time alkene will be major. This will be major product. Next, if you have Br, secondary position, and you have cyanide, Cn minus, you will do SN2. Heat is not given, so you'll go for SN2. If you have Cl and you have been given ACO minus Na plus, so again SN2. If you have Cl with ammonia, SN2. Clear? And if the same reactions, if I give you in terms of heat, same reactions, but this time with heat, delta, delta, and delta. Okay. Now these two will be changed to E2, but acetate usually have major product as SN2 only. It will hardly be used as base. Right? It will be hardly be used as base. Next, if you have Br with ETOH and heat, so you'll get this as double bond. And if you have uh, Br with only ETOH, no this one, so it is SNO. So here it will go via SN. Done. So these are typical cases, tertiary, secondary, and primary cases where you need to address. Okay. So in which case, whether it will become positive or negative, that is what we need to check and address that. Everybody clear on that? Right. And everyone. So I think this is how much you need to learn it from this topic. Okay. Uh, I have uploaded